7 students in the class. Okay, we continue with our lecture. Let me know if you're not able to see PowerPoint slides. I'm showing you a PowerPoint slide with a table. Let me know if you're not able to see the PowerPoint slide. Let me know. Okay. So last Friday, before we end our class, we already go through this table. Okay, what happened if you have subsonic flow, and what happened to the velocity? Okay, in the converging passage. What happened if you have a more than Mach number in your upstream velocity? What happened to all these parameters? Diverging also. Okay, and the equation is referring to this table is referring to this equation. dv over dv over v equal to negative dA over A 1 over 1 minus MA squared. So this table is built based on this equation. All right. Now I will go a little bit fast today. So the next question is that it is possible to reach Mach number 1 at here at center of the duct, or sometimes we use maximum minimum area. With this, if you have this configuration, if you have CD duct or converging diverging duct, this is called converging diverging duct on the left. This is diverging converging duct, if you see the label here. Okay, so the central area here, it can be maximum. It can be maximum if it's a diverging converging duct. If it's a minimum when it is a converging diverging duct. So the question is, it is possible that you reach Mach number 1 here if the upstream velocity is subsonic and y. Okay, if the upstream velocity is subsonic. So this question, you need to refer back to this table or this equation. So it's more easier you refer to this one. So if you refer to table, all these are calculations. So you go and read from the slides later on. All right. Now, in the isentropic flow, Mach number 1 can only happen in converging diverging duct in minimum area. Okay, minimum area. So if you look at your handout, question 31, it asks you, it is possible to reach subsonic, or not subsonic, sonic flow, Mach number 1, at maximum minimum area. So this one, the answer is only happen in minimum area. Okay, minimum area. So supersonic flow, sonic flow Mach number 1 cannot happen here. Okay, cannot happen here because the speed will slow down if you have diverging duct here. So you come in with the subsonic flow, which mean Mach number less than 1 on the left hand side. You go inside there, you'll slow down. Okay, you will slow down. Okay, so if you don't understand, you go to this table, right, where we go through so many times for the last Friday. Okay, if you look here, if you're going in a diverging passage, your velocity will decrease. If your Mach number less than 1, your velocity will decrease. So if your input here, you start with the subsonic, it is less than 1 from the left into right, you're not going to get Mach number 1 at here. But however, if you do the opposite way, if you have a converging passage, it means large area into small area, and you go in with the subsonic flow with its Mach number less than 1, your velocity going to increase in this case. So you have a possibility to reach Mach number 1. Okay. So these are the logic. These are the fundamental logic that might be evaluate or might be testing you in the coming exam. So just to see whether you're aware of this or not. Okay. So only happen in an isentropic flow. Mach number 1 only happen in this configuration only when you have a converging duct. Happen in a minimum area. Okay. Okay, the rest you can read. All these are from the calculation. Then another parameter we're going to look at today is DVHT. HT means throat. So central area here of this duct, we call it throat. Throat. Okay. We did not label this area as TH. Throat. Throat. Okay. All right. The rest you can read from my slides. So I'm going to go through some strategy when you have a compressible flow. Okay, we have a compressible flow. If your Mach number less than 0.3, then you have an incompressible flow. If your Mach number more than 0.3, then you will have a compressible flow. There's a slide, so let me show you. This one. So this slide we did go through last week. If your Mach number less than 0.3, you have an incompressible flow. If your Mach number more than 0.3, then you have a compressible flow. If your Mach number less than 1, then you have a subsonic. More than 1, you have a supersonic. Okay. All right. Now I'm going to ask question. Okay. Su Jinghao. Su, you are there?
Yes.
Okay, Su Jinghao. From Mach number, how do you know that the flow is compressible? How do you know from your calculation you are having a compressible flow? Look at the Mach number. What's the value that you should have if you have a compressible flow? Okay, the next one I'm going to ask Praka. Praka, stand by for answer. All right. So what is the value of Mach number that we are looking at if we have a compressible flow? Praka, what do you think? What is the value?
If more than 0.3, it's all compressible flow.
Correct. All right, good, very well. Su Jinghao, I just mentioned this slide just now. Okay, I know that this is a very early class. This is very important information. If your Mach number less than 0.3, then you have an incompressible flow, which is you use equation from chapter 1 until chapter 5. So if your Mach number more than 0.3, then chapter 6 equation come into place. Okay, so start from I think when we start chapter 6, when you answer question in exam, always start with the Reynolds number, find Reynolds number, then look at the speed, then define the Mach number, whether this is a compressible flow or incompressible flow. Okay, this is just a safety steps when you do your exam paper later on. Okay. We're going to look at strategy when we solve chapter 6 question, especially when it comes to compressible flow. So we're going to look at stagnation state with this P0 T0 that we introduced to you last week. Okay, the ratio between temperature and pressure. Okay, so when we look at compressibility, compressible flow, we will look at stagnation state and the entropy at that particular point. Okay, the first thing, look at the Mach number, whether it's compressible or not. If it's more than 0.3, then you have a compressible problem. When you have a compressible problem, the next step is you look at stagnation state with this the ratio of P0 and T0, which is the chart that you need to look at. Okay, the next one is this one you read through my slides. All these are mathematics conversion. I'll not go through. You read through all these you read through. Okay. This is the first equation for today, very important. The derivation I won't go through, but at least you know that the T over T0 equal to 1 over 1 plus K minus 1 divided by 2 Mach number square. This is the first equation for today. It's very important. Why this important? Because we have a T over T0 with the stagnation temperature. We will use it when we come to compressible, when you have a compressible scenario. Okay, so this is the first equation that is important. This is important. If you look at your tutorial or hands out, page 17, there are 3 equations there. So that 3 equations are very important. The first equation is what you see on the screen now. T divided by T0. This is a T ratio in the stagnation term. Okay, in a stagnation term. So this is the equation what we will use when we have a compressible problem. Then the second equation is the pressure ratio. The center term here is the same as previous one. What is different is the exponential component here, K divided by K minus 1. Okay, so you only need to memorize the pressure ratio, temperature ratio, and density ratio, the 3 brothers that we introduced last week. The differences is the exponential component here. Okay, the first equation for today is this one, T divided by T0 equal to something. Okay, and again, when we use this equation with the T0 is when we have a compressible problem, which means your Mach number more than 0.3. Okay. The second equation is the ratio of P divided by P0. So the differences is the exponential K divided by K minus 1. Okay, derivation you can see, you can read from my slides. The third equation is the density ratio, which you can see in your tutorial hands out, page 17. Okay, so it's a density ratio, and at the stagnation stage equal to the same as the temperature ratio just now. Only different is the exponential 1 over K minus 1. So there are 3 important formula that will help you to solve compressibility problem. So the first one is this one, T divided by T0. Okay, at least in your mind, you know that, okay, this is the equation we are going to look at when we have a compressible problem. Okay, so I don't expect you to memorize this one, but at least you know which equation to use. All right, so for compressible problems or compressibility problem, then there are three equations that you need to use. T over T0, P over P0, and the density. Density over density stagnation. Okay, these are the three equations that you can see on your tutorial or handouts, page 17. Yeah. Okay, just to have a quick question. Let me ask Joshua. Are you there, Joshua?
Yes, sir.
Okay. Just a quick question. When do we use this equation? When do we use this equation? Or this equation? When do we use P over P0? Or when do we use T over T0? When do we use these three equations? The next one I'm going to ask Vina. Vina, stand by for answer. If Joshua not able to answer.
To find out the Mach number, sir.
In what scenario? Is it all these three equation? Rho over rho 0 with the stagnation, P over P0, and T over T0. So in what kind of case we're going to use these three equations? Do we use this one in the incompressible scenario or compressible scenario? Okay, I'll let Vina. Vina, are you there?
Yes, sir.
Okay, so these three equation, T over T0 with the stagnation temperature, or P divided by P0, or density over density 0 with the stagnation. When do we use these three equations?
To find the ratio.
Yeah. We know from mathematics is find ratio. In what scenario? We use it in an incompressible case or compressible case? Let's say you have two kind of flow. You have an incompressible flow and compressible flow. So in what case you use all these three equation with the 0 at the
I think compressible flows.
compressible flow? Okay,
Yes, sir.
so you need to be confident. You need to be confident. Yes, the answer is we use these three. You use these three equation. T, yeah, for compressible flow. P divided by P0. As long as you see P0, we use it for you see the sub node of 0 means stagnation. Stagnation means doesn't move. The velocity equal to 0 at that point. Um, we use this tree when we have a compressible scenario. Okay, still back to a very simple question. Joshua, just now you're not able to. Where's Joshua? Okay, Vina, you are done with the question. I'm going to ask Joshua. What happened to Joshua? All right, Joshua, are you there? Not sure what happened to Joshua. Okay, Joshua, are you there?
Yes, sir.
Okay, how do you know that you have a compressible problem? Just now you mentioned Mach number, right? So what value that you're looking at if you have a compressible problem?
If Mach number is less than 0.3.
Less than 0.3 become compressible? That is your answer, is it? Do you mean that if you calculate and then you find that, oh, your Mach number is 0.15, that is what? That is compressible?
No, so compressible is more than 0.3.
Correct. Okay, very well. Okay, we continue with our lecture. So important, these three equation, P divided by P0, T divided by T0 with all these K and Mach number. As long as you see T0 or P0 or density 0, all these, if you see this, if you see that the flow is compressible, then we need to use these three equation. So the derivation you can read from my slides. All right, now what is important is the T versus S, like what we mentioned last week. So why we need to focus on the stagnation point? Because at stagnation point, our entropy is constant. Our entropy is constant when we have a stagnation point scenario. And this is another diagram that you have in your hands up, question 39. So you will see the line here. So let's say we have a nozzle, 0.1 and 0.2. So 0.2 is converging within, which means that your area is decreasing. And if you look back at the table that we go through last week, you know that if you look at the temperature, because we look at T versus S graph, T is the temperature in Kelvin, S is entropy. So if you look at T0, T1, and T2, T0 is a stagnation. T1 is a bit lower than stagnation. T2 is further lower than T1. So mean that the temperature is decreasing. Temperature is decreasing. That the relationship 1 to 2 decreasing, you can look at the table last Friday. So what you can see from this diagram here is that when a flow from left to right through a nozzle, through a decreasing area, you see that the temperature will be decreasing. Okay, the temperature will drop, because if you follow the solid line to the left, you will see that the value of your T is decreasing. Same with your pressure also. Okay, same with your pressure. So stagnation pressure will be higher than 0.1. Stagnation pressure at 0.2 will be lower than P1. So if you see this diagram, it summarizes what happened if you have this kind of setting. One thing interesting I want you to focus is the entropy always the same. If you look at this straight line, if you further this one, you have only one value of your entropy for all these points. Stagnation, 0.1, 0.2, all the parameter for 0.1, 0.2 will be the same at one entropy value. Okay, this is the important part. Okay, again, you see this equation again. We have a isentropic flow. We have a compressible flow. Second equation that we go through just now. And you see the different only the exponential component here, k divided by k minus 1. Okay, and then the density also. So when you have a Mach number at 1, the scenario is called chalk flow. So you have a chalk flow there. Okay, so when you have a chalk flow, we use this denotation star. Okay. And if you, for air, you can test that. If you substitute all the value there, for air, your K equal to 1.4. If you substitute 1.4 in the last three equation that I showed you just now, and then your K is 1.4, your Mach number equal to 1, right? Mach number equal to 1. Right? Every time you see P0, P0, rho 0, all these happen at Mach equal to 1. Huh? And also not necessarily Mach equal to 1, but every time when you have a Mach equal to 1, you can, in the equation, you can use the star sign for the top parameter. Okay, every time you see you have a case to analyze at Mach equal to 1, you can change this equation with the asterisk on the top. So this is the strategy when we solve problems. Okay, so this equation help you.
Sir,
Yes.
so we no need to calculate the Mach number.
No. You need to calculate Mach number when you don't know the Mach number at that particular location. So you use the first equation. You use the previous 3 equation to find. And then if the question asks you if you have a choke point, the keyword is choke point. So if you have a choke point, meaning that the Mach number at this location equal to 1. So when you have equal to 1 case, straight away you modify this equation with the star here on the top, and then Mach number in the equation become 1, equal to 1. K, you refer to the table 1.8. Depends on the medium that you're using. If air is 1.4, okay, clear. So there are 2 important things just now. For the last, I think, 20 minutes, we are mentioning about P over P0, T over T0, density over density ratio with all the equation, right? All the equation. All these 3 when we have a compressible question. And every time when we ask you about a choke point, straight away you modify all this equation with the star for the top parameter here. For example, this is we look at pressure, then we change the pressure, change the top parameter, and then the Mach number inside the equation will become 1. Every time we ask you about the choke point, right? Every time you see this choke, or another keyword we will give you, find the parameter at critical state. Okay, so we'll use a star sign in our calculation. So every time you use star sign, meaning equation inside that you use the Mach number equal to 1. You're going to simplify your equation. Okay, this is just an illustration. What happens if you have if you are using air, right? You just substitute 1.4 for air, Mach number equal to 1 in your equation. Yeah, there are 2 important points for this morning. Okay, and you can see this is a temperature scenario, and then we convert. Now this is the important slides. I want you to show you is that now this is an important equation that I highlight on the screen now. Make sure you write somewhere in your notes. So this is the conversion that we use, because in the equation between these three good friend, temperature ratio, density ratio, and pressure ratio, the equation on the right hand side always the same. Only different is the exponential component. It is here. It's always different. So on top of this one, you don't see anything. Actually, it's 1. P power is not 0. It's 1. So the only difference is K divided by K minus 1, K and 1. So you can do conversion. If you have pressure in the question, then you start with the pressure, convert into density, convert into temperature. So this three relationship is important for chapter 6. Okay. then you do conversion, right? So again, I repeat for this chapter, if it's a compressible, you look for P over P0, T over T0, density over density 0. And then if you have a choke point or critical state, your Mach number equal to 1. So you change everything inside the equation, become 1, and then refer table for K, right? Table 1.8, for example, for K, for the medium. Air is 1.4, for example. Okay, then you substitute inside the equation. And then in the equation, you modify the pressure ratio into P star. If you write P star, it means that it's a critical state. Below always stagnation because we look at compressible state. Same with the temperature. You just modify accordingly. Okay. Okay. What we are talking now is that the strategy in solving compressible problem. Okay. The first one, check your Mach number. Then you go to the equation. If Mach number more than 0.3, you know that this is a compressible problem. Then you straight away use stagnation pressure, stagnation ratio, pressure, temperature, density with the equation, right? And then you modify it from these three relationship with the exponential, all this. You just move around all these exponential. And then when you come to critical state with the Mach number equal to 1, then you modify the equation. On the top one, you modify it to star. Star is just a marking saying that you are looking at critical state, and the Mach number equal to 1 for this case. Okay. Right, we look at one example. Very quick. Okay, and then we go for a short break. So this example is in question 41. We look at converging duct. This is converging duct, right? So how do you memorize converging duct? The shape is that if you're converging the word C, right? The C, if you use your finger, your hand, C is like that, right? It look like that. So it's from the big area into small area. So this is how you memorize, right? So converging duct pass air steadily from standard atmosphere condition to a receiver pipe. This is a receiver pipe. And the flow is from the left to right. So of course, this one is, if you're in the rocket, is in other direction. So this is just a tutorial question. So the flow from the left to right, from a converging duct into receiving pipe. Again, this question is for question 41 in your handout, in your tutorial handout. So throat minimum flow cross-section area is given here. So this is the minimum. A is given here. Okay. Receiver pressure is given. You have two cases. So one cases is A, 80 kilopascal here, 80 kilopascal. For case A, later after you finish for A, you do B. You will drop to 40 kilopascal. What happened to the other parameter? Okay, determine the mass flow rate with its m dot. Again, recall what is m dot, rho AV. M dot equal to rho AV. Through the duct, which is here, sketch temperature entropy diagram. You need to sketch T versus S diagram. Okay, how do we solve this one? So I'm going to show you how we solve this kind of question. All right, so these are the parameter we look at. We're going to look at mass flow rate and we're going to sketch a temperature entropy diagram. Okay, now when we solve question, we always like to draw a diagram. So we draw out the setting of our system. We start with the standard atmosphere from the left. The flow is flowing from the left into right, and we go through a converging duct. And every time you see a converging duct, refer to the table that we go through last Friday. It will help you to have some sense on the velocity, temperature, pressure, right? So it will help you to double check your answer. Then you have a receiver pipe here. Right, we start with the equation of mass flow rate, m dot equal to rho AV. This one, I think all of you already know. M dot equal to rho AV. And because we are interested to find what is happening to the throat here, so we're going to modify our equation with the denotation of TH sub TH. So I'm going to use X then sub TH. It means it referring to this area. So we modify the mass flow rate equation, m dot equal to rho AV, and all this with the subnode of TH means what happened to the throat here, m dot equal to rho AV. And we want to determine the velocity. So again, we can modify with this. We don't know the parameter here. We need to find it out. So these are the steps to find the velocity. So we know that the Mach number equal to velocity divided by speed of sound. And this one need to be careful because this one will change according to temperature, density, and also so on. So there's a table to refer. So I already show you which table to go through last Friday. So be careful on the local temperature, local speed of sound. So if you modify this equation, ma equal to upstream velocity divided by local speed of sound, you modify into v equal to Mach number times the speed of sound, and c equal to square root of RTK. This one we gone through so many times, right? Your c equal to square root of RTK, and you modify, and you modify. So from mass flow rate equation, we modify in terms of Mach number and RTK. And recall that these three equations that we mentioned, I think 30 minutes ago, these three equations is very important when we have a compressible problems, especially when you see a nozzle like that. Nozzle, always you will look at these three equations. At T over T0, P over P0, density over density 0, stagnation. And the differences is just the exponential parameter here. So T, you have not is power 1. Okay, is power 1. P is K divided by K minus 1. Density equal to 1 over K minus 1. Yes.
How do you know it is? We want to use this equation because we not yet get the Mach number also.
So since we do not have the Mach number, but there's a keyword there. Every time you have a converging duct or diverging duct, most of the time you need these three equations. So this is another information for you. All right. So every time you see you given a diagram like that, you have a change of area of a certain pipe or something, then it also lead you to these three equations. Yeah.
Okay.
So this is another like highlight. Another highlight, because yeah, like you say, we don't know about Mach number, but when you have converging, diverging duct, most of the time we will call out these three equations. Okay. All right. Now we modify this equation, these three equations, T over T0 to a throat area here. Okay, so we would modify this equation on the left with a subnode T here. Right hand side continue the same, only we just want to make sure that we're focusing on the correct area with this throat here. So we just add the TH just below the temperature there. Same with the pressure, same with the density. So we'll just call out these three equations, then we modify a little bit. Then we continue with our calculation. Okay, so we assume that we have an isentropic flow and it behaves as ideal gas with constant CV and P. And this scenario, if you see the equation on the screen here, you see a star, it means that it's a choke point. And when you have a star, means that your Mach number inside all this equation here equal to 1. Mach number inside here equal to 1. And because we are using air, your K value in table 1.8 is 1.4. Okay, you substitute Mach number 1, K 1.4 in all these three equations. Again, every time you use Mach number 1 in these three equations, you need to modify your equation with the star on the top for all the top parameter. So these are the strategy we solve. Okay, every time you use Mach number equal to 1, you modify the term above the ratio here, become a star. And then the rest is just a mathematics statement. Like for example, you have a column, K equal to 1.4 means that you are looking at K value 1.4 and at the choke point or critical point, Mach number equal to 1. You substitute the value there, you'll get 0.528. So you modify because and from here you can further develop your equation. You can pull your P0 stagnation pressure here. You can modify it into atmospheric pressure. Okay. So try to digest what you see on the screen now. So what we do is that we move our P0 on the left to the right, and then we equal our P0 equal to atmospheric pressure, which is here, because you are given P atmospheric here. Okay, now, okay, so we have this equation come out. P ATM or atmospheric equal to stagnation pressure. Yeah, try to understand the logic behind all this symbol. So this slide just show you how do we make full use of the three ratio equation here. Is that we will analyze on the critical state, although the question do not ask us to analyze, but for chapter 6 question always go like this. There's a SOP already. So mean that we will
Sir,
yes.
if it is like in critical statement, the Mach number always in 1, right?
Correct.
Okay.
Correct. Yeah. So yeah. So yeah. Okay. So you just modify the equation, and you continue with the calculation because the atmospheric pressure was given 101 kilopascal, absolute velocity, absolute pressure. So you times the 0.5 times the 101. For example, in this example, you're given the atmospheric pressure equal to 101. So you know that from this calculation, your P star or your choke point happen at 53 kilopascal, Mach number 1. Meaning in the experiment, if you measure, if your temperature, if your pressure drop until or increase until 53.3 kilopascal, you're going to have a choke point. You're going to have a critical state. Okay, yeah. All right. Go and look at next slides. So we already find the critical number for our pressure. It means our critical pressure, assuming the shock will happen. When shock happen, right? Mark number 1 with the star, at this pressure 53.3. You do the same, so there are some statement here. So if your receiver pressure P sub RE, receiver, and you have, if your receiver pressure is larger than your critical value, so in this case, let's say in this calculation, your critical value is 53.3 kilopascal. So if your internal pressure or receiver pressure here is more than 53.3, let's say your pressure inside receiver here is, let's say, 100 kilopascal, let's say, what does it mean? It means your pressure at throat here, your throat here will be equal to 100 kilopascal. Okay, I repeat. So there's a statement. If your receiver or your container pressure is more than what you calculate just now, more than the choke point, more than the pressure at choke point, 53.3, the pressure at the throat area here will be equal to receiver pipe, will be equal to the container pressure. For example, in this case, in your calculation, your P star is 53.3 kilopascal. So let's say your receiver pressure here is 100 kilopascal. So based on this statement, your pressure at throat will be 100 kilopascal. Yeah, very important. Okay, the next scenario. If your receiver pressure is less than your critical state, you know that your critical state is kilopascal. Let's say you only calculate let's say your inside tank here, you only have 40 kilopascal. Your throat pressure here, will be equal to choke point. Will be equal to 53.3 kilopascal. So this is a very important statement that will help you when you analyze converging diverging duct. Okay, just now is PE more than your choke point. Let's say, your inside there is 100 kilopascal. Your throat pressure will be 100 kilopascal. But if it's less than the choke point, then the throat will follow the choke point pressure. Yeah, so this is an important understanding, basic understanding. If you refer, that is why we need to find a critical value. What is the critical value for pressure, density, or temperature? Most of the time we look at pressure. Okay, so if you're given the internal pressure, then you compare with the critical pressure, what happened? Then it will tell you what happened to the throat. Yeah, all right, so I'll just repeat. So if let's say you define your P star or critical value at 53.3, then you look at the receiver pressure or internal tank pressure. Okay, then you can predict what is the throat pressure. Okay, I'm going to ask question based on this statement. Let's say you have an internal tank here. I'm going to ask what is the pressure at throat in this case. So let's say your P star you calculate is 100 kilopascal. Let's say in calculation. And your tank, your internal tank here, let's say your P tank. Okay, if P tank equal 200 kilopascal, what is the P throat here? Okay, so if in your calculation, if you're in your calculation, you calculate P star equal to 100, and you're given the internal P pressure tank, the pressure inside the tank is 200 kilopascal. So what is the throat? Okay, I'm going to ask someone. So the question go like this. If in your calculation, you calculate the P star critical state happen at 100 kilopascal, and the internal tank pressure now you measure at 200 kilopascal. What is the value here? What is the value of the pressure at T throat? Okay, I'm going to ask question. Okay, Bila, are you there? Bila? Muhammad Bila?
Yes, sir.
Okay, so look at the slide now. So if you calculated the P star critical is 100 kilopascal, and inside the tank here is 200 kilopascal. So what is the value of throat?
So in this case, when the receiver pressure is more than the pressure choke, then the what's it called, the pressure inside the system will become the same as the pressure receiver. So in this case, it will be 100 kilopascal.
100?
200.
Oh, 200.
Yes.
Correct. All right. Excellent. So, all right, good. All right. Okay, I assume the rest you understand. Okay. Now, okay. So again, based on this statement, you know that what happened to the throat pressure. So in calculation for chapter 6, we know that all our temperature will be dealing with K Kelvin. So this is a simple calculation plus 273. Right. So because we know that when we have stagnation cases, our entropy always come into picture. Our S value, S unit equal to joule divided by kilogram dot Kelvin. So it's always safe to convert all the temperature in Kelvin. Okay, we continue with the scenario. Now, in your calculation, your P star equal to 53 kilopascal. And for first scenario, your inside here is 80 kilopascal. So what is the throat pressure? All right. So 80 kilopascal is more than your critical, which is the first case. So the throat here, the pressure throat here will be equal to the internal tank pressure. Okay. So your throat will be equal to your receiver pipe or the inside tank pressure based on this statement. Okay. So from here, you can find the parameter there. You can find the your Mach number. What happened to the Mach number? Let's see. Okay, so you substitute all the value. P throat you already find because based on this statement, you already know that your P throat in this case is 53.3 is equal to internal tank because internal tank is
it's 80. No.
sorry, 80 kilopascal. Sorry, so not 53. Huh? Not 53. 80. P0 we know that is equal to PATM, right? So the only parameter we don't know is the Mach number. K you know, 1.4. You substitute, you get Mach number at this region, at here. Mach at throat in calculation, textbook answer is 58 lah. Mach number 58. So we know that this number is subsonic less than 1, but it's more than 0.3. It's still compressible problem. Okay, yeah. So I think there's nothing complicated here. For the continue, you can calculate the throat the density also. The density also. This value is given in the handout. In your handout, this value is 1.23, and then you substitute all the value, you get what happened to the density at throat area. Same with the temperature also. Okay. Same with the temperature in Kelvin. Okay. Okay. Then you need to draw, right? You need to draw. So velocity you can calculate based on ma equal to speed of sound, square root of rho RT, and the value of RT you can refer to table 1.8. Table 1.8. So at the end you get your velocity equal to 193 in a unit of joule per kilogram square root, and already proved to you how you convert square root of joule over kilogram in meter per second. Okay, I already showed to you how you convert this one in meter per second. So in exam, the complete answer you must arrive at meter per second. Don't stop at here. Don't stop at here. You need to arrive at meter per second. And go back to the mass flow rate. You have rho at throat, area at throat. Area is given, right? Then velocity you calculated, substitute all the value, you get the mass flow rate. And this is the graph that we draw. And this one already I already given you in the handouts. Okay, it's just to help you a little bit to draw this table. Okay, to draw this graph. Of course, in exam, you are required to draw this diagram. Okay, how you draw this one? You draw, start with the temperature versus entropy. You draw T versus K, T versus S. Then the first one is the axis. Second one is a temperature line. You draw the temperature line. Then from there, you add in the pressure line, always slanted. All these points go through the same entropy point. Okay, go through the same entropy point. Then you input all the answer there. Right? And this answer in your handout is for case B. Yeah? Is for case B, which is 40 kilopascal. So I won't go through the B point. I think I'll show you how to use the graph. So I'm going to use this graph, isentropic table, or this figure D.1, which is in your handout, page 20. It will be same if you use the equation also. It's the same. So how do you solve this one? So let's say you get the pressure ratio 0.8, for example, in this case, 0.792. You enter the graph from the left, because this graph, you have 3 axes, right? You have 3 axes. On the left, you have P over P0, T over T0, density over density 0. Right? All these values apply to either this one of ratio. On below here, you have Mach number, and you have an area ratio here on the right. So all these lines represent a certain parameter. Okay, so this line is referring to area. Don't read the wrong line. This curve, special curve, is referred to area. This one pressure, this one density, this one temperature. Okay, so for example, we use the question 28. Let's say you find a ratio 0.79 pressure ratio. So you enter from the left. It's about 0.8. The strategy is once you find the ratio, you enter the graph from the left. Then you look at the parameter you want. So you go, because you are using the pressure ratio, so you use around 0.8 here. You go and touch the pressure ratio line. You go and touch the pressure ratio line, because this number will tell you what is the Mach number happen at this value. So from this graph, straight away, you touch the pressure ratio line, you extend down, you get 1 Mach number. This line and this line in exam will give you at least 1 Mach. If you use a hard copy, you draw this line, go in, draw down, you get 1 Mach. To define that you understand, to use a diagram D1. So in this case, you get your Mach number is around 0.6. Okay, this is quite straightforward. You enter from the left, then go down. Then after that, because this is an important parameter, we are focusing on throat, so we stay at Mach number. Here we look at Mach number here, 0.6 around here. You continue, you extend this one, you will get your density line, you will get your temperature ratio here. You extend to the left, you'll get all this ratio value. Okay, for example, I show you with the green arrow at the same Mach number, because we are looking at throat scenario. At throat, you know that your Mach number at throat is 0.6. So 0.6 touch the first line here is a temperature ratio line. Here you get 1 number for temperature ratio. In this case, 0.9, about that. Then the sky blue line touch the density, you get the density ratio about 8.5. You substitute all the value, you'll get the same answer. Okay, you still get the same answer. Cool. So there are 2 methods. One is use equation. Second one is use diagram. Okay, equation like P over P0, T over T0, density over density area, so on. Second one, you use diagram. Okay. Of course, if you use diagram, there's a human error when you plot graph because the resolution will define the accuracy of the answer. Okay, yeah. So this one you can go to right. Okay, this tutorial question you go through at your free time is important to go through. I won't go deep into this sample. Read through. Read through. All the steps are there. Read through. This example is using graph to find answer. Okay, I won't go through. Just go through all this example. Again, there's a typo error. This is not R. This is K. Kelvin. Temperature is in Kelvin. Okay. Just make a note, a small note. Temperature here is not R, it's K, Kelvin. All right, so we stop at this example. Again, tutorial question 44. You need to go in. You need to study it at your free time. It's important for you to go through as many examples as you can. So this is another example. We apply the 3 equation this morning. Okay, I'm going to stop the recording.